Hello everyone, welcome back to Pseudocoder. Those who all are new, my name is Ravina. I am a software engineer and I solve algorithm problems. I also have a data structure series, so be sure to check it out if you are new to coding or just want to learn how to apply those data structures in competitive programming or just programming in general. So today we are going to solve problem number 22, which is generate parentheses. Let's start by reading the question. It says that given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. So what the question means is that you'll be given a number. So for example, here we have n equal to 3, and then we have to create possible combinations, valid combinations of parentheses such that they are valid. So here you'll see that this is one of the valid parentheses where you have open bracket, close bracket, and then open close and then open close. So kind of a nested thing. Here we have two open close and then that is nested within this big open and close bracket. So basically you have to find out all the combinations of the valid parentheses based on the input number n. So today we are going to solve this using a more intuitive approach, which is backtracking. And I'll be drawing some boxes and going through and actually explaining how it happens step by step. So let's move on to my notepad. We are going to use example of n equal to 2. So what do we need for this? First thing, we are going to solve it using backtracking, and that is nothing but DFS. And let's see, what do we need? We need three things for the DFS function. We need number of left brackets, so basically L, the right number of right parentheses, which is R, and then a string S. This string is going to basically be the result as in the substrings inside the array. So we need three things for the DFS function. Now let's talk about what should be your breaking condition. Since you are using a recursive algorithm, the super important thing is to have a breaking condition, because if you don't have the right breaking condition, you can never reach the right solution. So the breaking condition here is, let's think about it. If I have n equal to 2, how are my combinations going to look like? One combination would be something like this. The other combination can be something like this. So are you seeing a pattern? You'll see that if there is n equal to 2, that means I have two opening brackets and two closing brackets. So that means each and every time with a valid string that I produce, that I create, I'm going to have 2 into n length of that string. So if you also look here, it is, two opening brackets and then two closing brackets. So that means it has to be 2 into n. So whatever array n is, if my length of s is equal to 2 times the length of n, that's when we know, oh, we actually found a string, and then we add it to our result. Since this particular this particular solution has a result, has an array, so we are going to create a result array and we are going to stuff all our strings in here. So to start with, what did we talk about? The first condition was if my length of s is equal to 2 into n. If that is the case, then I'm just gonna add it to my result. Now let's talk about the second condition. So my second condition here would be if I don't have the match, that means I still am gonna go on and create my, start building my string. So that means that I'm gonna first check if my left number of parentheses are those less than n. That means I can add more left parentheses. So the next check I'm going to do is if my left is less than n. If that is true, then I'll call the function, the DFS function, and what I will give it, I'll add one left parenthesis to it, and I'll also increment the count. So I'll call my DFS function, I will increment the count of L I will keep my right as it is because I did not really add anything. And then I'm going to add a opening bracket to my S. That's all that's all I need to do. It's gonna call the DFS function again. It's gonna, loop through it. Now, I have considered all my opening brackets. What about my closing bracket? So I'll have the last condition where my last condition would be if my number of right brackets are less than the left brackets. That means I need to add more right brackets. Remember here I'll not check if my right brackets are less than n because I want to match the number of right parentheses with the left parentheses. So that's why I'm going to check if R is less than L. Number of right brackets are less than number of left brackets. If that is true, then I'm going to simply call the DFS function. This time, what did I do? Did I touch the number of left brackets? No. So I'm going to keep it as it is. I added one right bracket. So it's going to be R plus 1. And then I'm actually going to add the right bracket. So it's going to be S plus the opening bracket. And that's all you need to do. That's all you need in the recursive backtracking function in order to work with this. So let's see this how we can, actually solve this with n equal to 2 example. So to start with, I'm going to have a L, which is 0, my R, which is 0, and then my S, which is actually empty. And as you know, I like to create a box for every recursive function so that it's easy for me to keep track of things. So I have this. Now I come in, I check, is my length of S equal to 2n? No, it is not. My length of S is actually 0 right now. There's nothing in it. So I'll go to the next condition. My next condition says if my left is less than n, my left is actually 0. So this is left, this is right, this is S. So my left is actually 0. That means it is less than n. So I'm going to call my DFS function. So I'm going to call my DFS function, which is right here. I am calling my DFS function with L is with left plus 1. So this is 0 is going to become 1. And then my R is going to stay the same. So it stays 0. And then my S is actually S plus opening bracket. Since my S was actually empty, it's going to look something like this. To make it, visually not confusing, I'm going to use curly braces here because opening and closing parentheses can become a bit difficult to understand. So I'm going to call my DFS function. Since this is going to get called, it gets its own box. In the box, what do we receive? We received 1, we received 0, and then we received an opening bracket. Okay, I'm going to the top. I'm going to the top of the function again. Remember, because it is calling itself. So I'm going to go to the top of the function again. I'm going to start at the top. If my length of my length of S less than equal to 2n, which is actually 4. So is my length of S equal to 4? No, it is 1 right now. It just has an opening parenthesis in it. So we move on. I check if my L is less than n. Yes, my L is actually 1, my n is 2. 1 is less than 2. What it does, it calls the DFS function again. So I am going to call the DFS function again where L becomes L plus 1. So this becomes 2. R stays the same. And then a opening parenthesis is added. So you get this. Oops. Yeah. So I have two opening parentheses here. So I called a DFS function, so that needs its own box. So we go here, we create a box. The input was 2, 0, and then two opening brackets. I go up again. I check if my length of S is equal to 2n. That means my length of S is actually 2. Is it equal to 4? So 2 equal to 4? No. Okay, I move on to the next condition. Is my L less than n? My L is currently 2. Is 2 less than 2? No. Okay, move on to the next condition. I have my I'll check if my r is less than n. Yes, my r is less than n. It is 0 right now. So that means I need to call my DFS function. And what I'm going to do this time, L is going to stay the same, R is going to get incremented by 1, and there is going to be a closing parenthesis to my string. So my 2 stays the same. I'm calling the DFS function. 2 stays the same. 0 becomes 1, my opening parenthesis, and then I add a closing parenthesis here. Okay, I keep using the opening parenthesis. Yeah, so since I called my DFS function, it gets its own box. So I have it here. I got 2, 1, this, and this. Okay. Uh, I go to the start. I check if my length of S is equal to 2n. So my length of S is actually 3, 2 opening brackets and 1 closing. It's not equal to 4. So we move on. Is my L less than n? No, my L is 2. N is 2. 2 is not less than 2. We move on. We come to the third condition. Is my R less than n? 1 less than 2? Yes. That means I call this function again. So I call my DFS function. I keep my L as it is. I increment my R by 1. So my R becomes 2. My my closing bracket gets added to the S. So it becomes like this. I go to the, since I'm calling it again, it's going to get its own box. It's going to be 2, 2, and something like this. Okay, I go to the start. I check is my length of S is equal to 2n. So this time my length of S is actually 4. It's equal to 2 into n, which is actually 2 into 2 is 4. That means this particular string gets added to my result. So I'm going to add this string to my result. So it's going to be this. And one more thing, once you add it to your result, you don't need to actually process anything. So what you can do is you can simply return. So when you return, it's going to go back to its previous cursor. And for us, it goes from this box to this box. Now, if you look at it, this when it goes to this box, this was actually we added an closing parenthesis here. That means this particular method was executed. This particular if loop was executed, and this is the end of the method. So that means we are already at the end. We'll go back to this cursor. When we go back to this cursor, it was actually also at the end of the DFS, because you see we added a closing parenthesis here. So that means we already reached here, which is the end of the method. We will go back. Once we go back, we come to this particular instance. Okay. Um, here, what we are going, here we were right here when it called. So the next thing that we have to do, since, I can determine that because I added this particular string was opening parenthesis was added to the input. This is the input. And so I know that this particular if loop, the second if loop was executed. Let me actually rub everything off so that we can do, you don't get confused. Okay, so we are here in this particular box right now. Here, what was the input? It was 1, 0 in the opening bracket. We go to the next if. We check, is my R less than L? Yeah, my R is 0, my L was 1. So what do? We call this particular DFS function. So it gets its own box, right? So we will be creating a new box, which is gonna be, okay, so first we write our DFS call here, which is gonna be 1. My left stays the same, my right becomes R plus 1, and then my string actually becomes string plus closing. So I already had an opening bracket, I add a closing bracket. So that is gonna be my DFS call. So what do I get? I get 1, 1, and this. I go to the top of the function. I check, is my length of S equal to 4? No, it is 2 right now. I just have one opening and one closing. I go to the next condition. Is my L less than N? Yes, my N is 2, my L is 1. 1 is less than 2. I'm going to call my DFS. So I call my DFS function. What do? I do L plus 1. So 1 becomes 2. R stays the same. And then I add an opening bracket. So I have this string, and then I have a opening bracket here. Since it's a DFS call, it gets its own box. We have 2, 1, and this. It goes to the start of the method. It says, it checks, is my length of S equal to 4? No, it is 3. Okay, moving on. Is my L less than N? No, my L is 2. N is also 2. 2 is not less than 2. We go to the next if condition. Is my R less than L? So let's check. My R is 1, my L is 2. Okay, yes. So that means this last DFS function gets called. So I have a DFS function. L stays the same, so 2. R increments, so R becomes 2. And then my S, a closing parenthesis gets added to the S. So like this. Since it's a DFS function, it gets its own box. It is 2, 2, and this. Oops, yeah, this. So it goes to the start of the method. We check, is my length of S equal to 4? Yes, my length of S is equal to 4. That means I add it to my result. So my result is gonna be this now. It has one more additional element, and then I return. So when I return, it's gonna go from this box to this box. Since this was already the end of the method because we added a closing parenthesis here, it's gonna go back. Now we check, is my R, once we are in this box, we check, is my R less than L? No, my R is 1, my L is 1. So we go back to the previous cursor. We are here. We already have exhausted my left, my right, because these were the two conditions and these were the two recursive methods that we called. So we are at the end and we go back to the main call. And here, when we come back to the main call, we have actually exhausted all the backtracking patterns. So that means that whatever we have in our result array is the solution, is the result that we wanted. So I hope this explanation was helpful. Let's see how we can convert this into code. All right, so the first thing that we need is a DFS function. So we are going to define that. It's going to be definition of DFS. I have my left, and then I have my right, and I also have my string S. The first condition was to check if my length of S is equal to 2n. So that's what I'm going to do. Length of S, if it is equal to n into 2. If this is true, then I add it to my result. I add my string to my result. And then what do we do? Once we have a match, we just return. My next if condition was that if my left is less than n, so my left is less than n. If this is true, then I'm going to call my DFS function. I'm going to increment my left. I'm going to keep my right as the same. And then I'm going to also alter my s. So I'm going to add my opening parenthesis here. So that's what we did for left. What did we do for right? We checked if my right is less than left. That means I need to add some closing parentheses here. I call my DFS. I keep left as it is. I increment my right count. And then in the end, I add my closing bracket to my string. That's all the DFS function does. Now, what did we need? We needed a result array to store our result, and then we do a DFS call. How did we call it? We called it with left 0, right 0, and string as empty since we did not have anything at the moment. And then in the end, what we do is we just return results. Let's see, we can run it. Okay, let's submit. Yeah, as you can see, this one is accepted with acceptance of 84%. So let's talk about the space and time complexity of this particular algorithm. The time and space complexity of this problem is a bit complex to calculate. So let's see, I'm gonna use my notepad. So here, think of it as a binary tree. It's not going to be exact time and space complexity because as you might have seen from the solutions, it's pretty vague. So we are going to do it in a simple way. In the DFS function, you'll see that we have two things. We have two DFS calls, sorry. One is for the left, where we are adding left plus one, and the second is when we are doing it for the right. So it means that it's going to be, bifurcated into two. And if you look into it, time complexity wherever you have something which is, just splitting into two, splitting into two, splitting into two, it becomes, the time complexity actually becomes 2 raised to n. And this is very similar to what we have right now. Here we have, left is less than n, right is less than left, which is here, So two if conditions. So since we have these two, we know that it's going to split into two. Each function is going to call itself two times. So that is where 2 raised to n comes in. Since our n here is actually 2n, if you look at it, n was 2, but we had to create a string where it was, four characters. So that actually means that n in this scenario, which should be actually this, is actually 2n. So that means that it is going to be 2 raised to 2n. So the time complexity of this particular algorithm is going to be 2 raised to 2n. Now let's talk about the space complexity. Since it's going to be, this is a backtracking problem, and this is a DFS problem, the space complexity is also going to be the same. We cannot just only look at the result that we are using, since this can store, any number of strings. The memory that is getting used for a DFS function is actually the time that it's the same as the time it's taking to process. So the space and time complexity of this particular algorithm roughly is going to be 2 raised to 2n, which is what you can an interviewer can expect from you, rather than having calculating some bizarre time complexities. As you can, let me actually show you what I'm talking about. So in respect to what they have here, 4 is to n divided by root n, no one expects you to come up with this. So I hope this explanation was helpful. The code for this problem is going to be on my GitHub channel, and I will actually mention a link to that in the description below. Please give me a like and comment. That really helps my channel. Click on the subscribe button if you want to see more of my videos. I also have some data structure videos coming up, so stay tuned for that. I hope you have a good rest of the day. Thank you so much. Bye.